So I'll just refresh our stereochemistry of alkenes. We talked about a couple chapters ago that we can use cis and trans, but a lot more useful are Z and E, because Z and E can work regardless of how many different groups you have on your molecule. So I just have to figure out on each side of my alkene which is my one group and which is my two group using Conninghold-Prelog rules, my one group and my two group, and then figure out where my one groups are and see if they're on the same side or not. And these ones are not, they're across, so it's entgegen. So this would be E. There's no way to talk about whether or not this is cis or trans because all four of these groups are different. There's a CH3, a bromide, a chloride, and a hydroxide on here. So we can't say which two are the same group on the same side. So again, that's why Z and E is so much more powerful than cis and trans. And we also previously talked about the fact that more substituted alkenes are more stable. So this is a tetrasubstituted, which is better than trisubstituted, which is better than disubstituted, which is better than monosubstituted, which is better than unsubstituted. So the physical properties of alkenes and alkynes are also going to be very similar. Boiling points are typically going to be low because the molecules are nonpolar. Since there's not really any polarity to the molecules, they're not going to have high boiling points because there are very few intermolecular forces. Also, they're typically only soluble in organic solvents because there are no hydrogen bonding groups to make them soluble in water. So soluble in organic solvents, insoluble in water. So we've already seen ways to make alkenes. So if I have a halogen and I treat that with a strong base, something like t-butoxide, I can eliminate that to form an alkene. And we also looked at if we have an alcohol, that we could either treat that with a strong acid, like sulfuric acid, to form an alkene, or in basic solution we could treat it with phosphorus oxychloride and 2 equivalents of pyridine, and that would also form the same alkene. And we saw that we can make alkynes from dihalides, but now we need a stronger base. Something like sodium amide. That can make an alkyne.